This is an example of an AC node solutions game in Circuit Tutor at level 2. As always, we have examples available here at a variety of levels of difficulty, and it's always a good idea to view some examples prior to attempting to work the problem. For right now, I'm going to go straight into an exercise on level 2, or the medium level. So our first task, as always when doing nodal analysis, is to select a reference node. If we fail to select a reference node, we would have no way to compute any of the node voltages because we could only compute then differences between them, and we want to have absolute values. So generally we want to select a node that is connected to many other many circuit elements. So for example, the black node has 1, 2, 3, 4, 5. We also want to connect to voltage sources where possible, and it does connect to one voltage source. The magenta color node also connects to 5 elements and one voltage source, so that's also a good choice. The others would be probably not as good since they don't have as many connections. So let's just use the black node here, and then we'll click OK. Okay, so because this is a solutions game, we are being given the Kcl equation for this circuit. We do not have to write that ourselves. However, we do need to determine the voltage constraint and sought variable equations for this particular circuit. So let's go ahead and do that. We'll start with the voltage constraint equation. And that will be for, let's do it for the voltage source V2S. And basically that's going to be a difference of node voltages. So we'll have that since we have V2 and V3 involved there. And that will be equal to the value of that source. And then we take V2S down here. That's 3 angle 180 degrees. And you may remember that 3 angle 180 is the same as -3 in rectangular format. But here I'm required to enter it in polar format. So I need to put 3 angle 180. If I tried to put a -3 here, for example, that would not be accepted because magnitudes of complex numbers, by definition, should always be real. So that has to be a positive number. Okay, now it's V2 is on the positive side, so it's going to be V2 minus V3, which is on the negative side. So we have to make sure we get the polarity correct on that. So let's check that equation. And that's correct. Now we also have a second voltage source here, V1S. So let's enter an equation for that. It doesn't matter which order we do them in. So V1S has one side connected to ground, or a reference node in this case, and the other side connected to a non-reference node. So we just need this term here. We wouldn't have anything to fill in if we use that term. So that will be equal to just the value of that source. And in this case, the negative side is connected to ground, and the positive side is connected to V3. So that means that this will just be V3 is equal to the value of that source, which for V1S, we find that down here, that's 2 angle 0 degrees. And always check polarity to make sure we have that correct. So again, V3 is on the positive side, and then it's basically V3 minus 0 if you want to think of it that way. But again, we can't enter something here because this won't accept V0 as a valid entry. Okay, so we check that. And that is correct for our second voltage constraint equation. Now we're going to enter an equation for the sought variable, which in this case is the sought current I0, which is the current through this 2 ohm resistor, as you see. So we'll select, and that's a branch current since it goes through one element. So we'll select sought branch current. And so we have I0 equals. And now because, again, this is a difference of 2 node voltages, neither one is the reference node. So we'll need this type of term here. And just using Ohm's law. So now we have to make sure we get the polarity correct. So because I0 is going into this side, that means this side needs to be the positive side in Ohm's law, right? So that's going to be V1 is going to be the number with the positive coefficient, and then it's negative V2. And that will be divided by the value of the resistance, which is just the 2 ohms. And again, always check your polarity because Ohm's law half the time, remember, has a negative sign in it. In this case it doesn't if I put the V1 here and the V2 here. If I'd switched those, then I'd have to put a negative sign here, or perhaps I could put it over here as you prefer, but not, of course, both places, which would cancel out. And any of those proper combinations would be accepted. Okay, so let's check that. And that is correct for the sought variable equation. So now I believe we've written all the equations we need for this particular circuit, because notice that the values of this node and this node voltage are constrained by voltage constraint equation, so we really only had one Kcl equation. That was for node 1 here. Okay, so we click No More Equations. And now the additional thing we have to do in a solutions tutorial is that we need to write these equations basically in a standard form. Not the sought variable equation, we'll use that one later, but just the voltage constraint and the Kcl equations. And by standard form, we mean a single number times V1 and a single number times V2 and so forth, and then a constant term possibly on the right-hand side, although this equation actually doesn't have a constant term. And then we enter these as well. Okay, so now in doing that, we are allowed to multiply through by a constant. So for example, if you wanted to clear fractions by multiplying this by 14, you would be welcome to do that, and that would work. However, what you cannot do is to, for example, substitute this equation into here directly, or into here, and make linear combinations. That's not accepted. We'll do that later when we do the algebra, but we're not going to do it when entering the equations into Circuit Tutor. Okay, so the first equation is fairly simple. It just says V2 minus V3. So V2 will have a coefficient of 1, and V3 will have a coefficient of -1. And of course there is no V1 there, so that has a coefficient of 0. And then the constant on the right-hand side is just going to be 3 angle 180 degrees. Now you may know that 3 angle 180 is the same as -3. If you think about the Argand diagram, right, the -3 is on the negative real axis, so the angle there would be 180 degrees. But here we're required to enter these right-hand sides in polar form, and notice that the coefficients here have to be entered in rectangular form. And that's really a matter of convenience because it'll usually be easier to enter them that way. So that's why it's specified the way it is. Okay, so the second equation is just V3 with a coefficient of 1 is equal to the constant, which is 2 angle 0. So we put 2 angle 0. Okay, and then the third equation is the more complicated one. So now we have to look for the coefficient of V1. And we have 1/7 V1. And as you may remember, that's equal to 0.1429 in decimal form. Then we have to add it to a half and to another half, so that altogether will be 1.1249 for V1. And then for the coefficient of V2, well, this part's going to be imaginary, so let's do the real part first, which comes over here. So that's going to be -1/2. So I'm going to type -0.5. And then this V2 term is actually going to be imaginary. So if we think about it, first of all, the minus signs could cancel out, so we just really have V2 over J7. And 1 over J, you may remember, is just -J, because J squared by definition is -1. So 1 over J is -J. And we also have to take the reciprocal of the 7. Sometimes people forget to take the reciprocal of the other number, but remember that in a reciprocal, both of these numbers are in the denominator. Therefore, we have to take reciprocals of both of them and multiply them together. That's just how reciprocals work, of course, in algebra. So we're going to have plus J times the value of 1/7, which is just the 0.1429, as I mentioned before. Now for V3, the next coefficient, that's just going to be -1/2, so I just put -0.5. And then the constant term here, well, there is no constant term in this equation, so that will be 0. Okay, so those should be the proper equations, so now we'll check those. Okay, and it looks like we do have an error there. And notice that all of the boxes here are turned yellow, regardless of which one, because it can't really determine which coefficient you've entered incorrectly. So let's just double check that. So we had the 1/7 v1, and then we had v1 over 2 plus v1 over 2, so that should have been a v1 and 1/7. So that should be correct. And then the v2, we had a negative 0.5, and we had 1 over j is negative j. Oh, I wrote that wrong. It should have been negative j because 1 over j is negative j. So that's where I made the mistake here, was on that plus sign, should have been a minus sign. And then the rest of that should have been okay, and then the v3 is negative 0.5. So we'll try that now. Okay. So let's triple check that then. So again, v1 is 1/7, and then we have 1/2 and 1/2. Those both have plus signs, so that should be correct. And the v2, again, negative, cancels a negative, so you have 1 over j sevenths, and that will be negative j times 1/7, so that should be good. And v3 is negative 1/2, and okay, I'm just going to use the cheat button to see where we went wrong. I forgot the imaginary term here. Okay, there was also an imaginary part for v1, and I neglected to enter that. Okay, so that was my bad. So I just simply overlooked that. I was so caught up with the real parts here, I forgot the imaginary part. So this term, and this term, that did indeed add to the 1.1429 or 1.143. And then here we have 1 over negative j7, and that is equal to 1 over negative j is j, so we have a j divided by 7, and 1/7 is 0.1429. So that is the correct coefficient there, and that should actually fix it now. Everything else was correct. It was just I neglected that one term. Okay, and that's one of the reasons you're given several attempts, because it's easy sometimes just to make a silly error like we did there. Okay, so now we have the simplified equations that are correctly written here. And the next job is we have to form these or cast these as a matrix equation. We're probably not going to really use a matrix equation to solve. That's not, at least what I would recommend, as the best way to do this. But we'll have it for reference if we wanted to use that. So this is easy to do. We can just click this copy from simplified equation. It's just going to take these coefficients and move them down here for us so we don't have to retype them. And again, what that really means is, for example, the first equation means, this means 0 times v1 plus 1 times v2 minus 1 times v3 is equal to 380, and so forth for the other equations. So for example, this one would multiply this multiplies this multiplies this to give you this constant. That would be the third equation. Okay, so let's check that. And now the next task is to actually solve these equations. Now there's many ways of doing this. Students often wonder how to do algebra with complex numbers, and the answer is you do it exactly the same way you would do it if all these coefficients were simply real numbers. It's just we have to do complex arithmetic now instead of real arithmetic. So the same techniques you learned in elementary algebra class work just as well with complex numbers as they do with real numbers. So we could do, for example, a formal Gaussian elimination on this matrix. That's usually, as I said, not the best method to do, at least in my opinion. But there's various methods that we can use. But I'm going to show you an elementary algebra method that involves simply substituting, because we really only have one complicated equation, and we can substitute these into here and just get a single equation in a single unknown. But we want to, anyway, find some way to solve those. Now your instructor might ask you to turn in that algebra written up for the problem. If so, then do that. If not, it would be a good idea probably just to have that for your own records, and when you're studying and going back over what you did, that would give you a record of that work. Okay, so now we need to compute and enter the values for v1, v2, and v3. We already know v3, it's given here, but we need to find the others. So for that, let's go do the algebra on paper. And I meant to just minimize that there. So basically here I've copied over the simplified form of the, let's scroll that a little bit here, of this third equation, which is the Kcl equation, the more complicated one. So I've just written that here, 1.143 plus j 0.1429 v1, et cetera, times v2 minus v3. So again, it's just transcribing that equation for the third equation, that is, this one. Okay, and the right-hand side was 0 there. I also know that v2 minus v3 is 3 angle 180, and I've written that more simply as just -3, because you remember on the Argonne diagram that -1 is equal to just 1 angle 180. So this is just 3 angle 180 is just -3. And I've also written that v3 is equal to 2. Again, you could write 2 angle 0, but it's not really necessary. Just write it in rectangular form like that. And so now, basically, I want to get rid of one of the two variables here. Or actually, I can get rid of two of the variables, I mean. So, of course, the v3 will just be substituted in, but I'll also solve this for v2. And remember, I'm getting rid of, well, I'm getting rid of v3. I need both v1 and v2, so it doesn't really matter which I solve for. So I've just chosen to solve for v2 here. And then that's negative, and of course I know v3 is 2, and so I can just subtract that and get that to be -1, or in polar form that's 1 angle 180 degrees. Okay, so we just solved directly here. In other words, we just combine these two equations to solve for v2. So now we know v2 and v3, we can plug those into this top equation. And so I have this times v1, which is the remaining unknown voltage. And then I'll just put everything else on the right-hand side. So I have the 0.5 v3 comes down here. And then the v3 I put in just a value of 2. And then I have basically this value I've subtracted here. Let's see. So yeah, that's subtracting from this. Oh, I see. That's right. I forgot I used, when I subtracted, I just changed these minus signs to a plus sign. That's what I did here. So I changed the minus signs to a plus side to put it on the other side. And then I multiplied by v2, which is -1. Okay? And then I'm just evaluating that, adding that up. 0.5 times 2 minus 1, of course, it's just 0.5. And then we have the minus j, 0.1429. We can do that in our head. And then now the last step we have to do on a calculator. So I'll pull up a TI-84 Plus emulator here to demonstrate that to you. And so we're just going to divide this by this. So we'll just enter that as, now before we do that, I should point out that we want our answer in polar form. So I want to make sure that my calculator is in fact in polar form. If it's in real mode, we can't do anything with complex numbers. So that wouldn't work at all. So I have to make sure that you go into modes and always make sure down here that you are set to, in this case, I want polar modes. I'm going to choose this. If you want rectangular mode, then you would choose this. And also, I like to work in degrees because that's what's demanded by Circuit Tutor. So therefore, I'm going to be in the degree mode. And that's typically what engineers use anyway. Okay, so we'll enter that expression now. And so we have 0.5. Oh, I'm sorry. Let's clear that because I forgot the parentheses. So I'll put the parentheses 0.5 minus, and the j becomes an I on the calculator. So that's second and a decimal point basically is the j, times 0.1429. Close parentheses. And remember, I do have to use parentheses around the complex numbers, of course, to be able to divide. Otherwise, the order of operations would mean I'd get the wrong answer. So divide that by the parentheses here of this coefficient. So that's 1.143 plus the I here times 0.1429. Close that parenthesis and hit enter. And that gives us the value of 0.4514, angle -23.08 degrees, rounding to 4 digits. And I want to keep at least 4 digits here just for the sake of accuracy. And remember, this did come out in degrees because I'm in degree mode, but always pay attention to what mode you're in because otherwise it would come out, of course, in radians if you're in the radian mode. Okay, so we have the value v1, and the other values we already know. So V1 here, I'll enter that as 0.4514, angle negative 23.08. Oops, forgot the decimal point. And then the V2, remember that's 1 angle 180. And again, I have to enter that in polar mode here, so I can't write -1 because it wouldn't allow a magnitude of a complex number to be negative. That's not a valid form of a complex number. And V3 is just 2, so that would be 2 angle 0. So that should be the correct values. And those indeed work, and they've been printed on the screen here. And then the next step is to use the SOT variable equation, this one, in order to compute the requested SOT quantity and enter it in the next form. So basically, I simply need to take V1 minus V2, which are written here, and divide that by 2. So that would be done, again, on your calculator. I guess I can illustrate that real quick. Okay, so I need to use parentheses again there. And then the V1 is the 0.45. Actually, I could just use answer there because that's what I just computed, so I'll just use answer. Minus V2, which actually I could just write that as +1, really. Divided by 2. Since a -1, of course, is just a +1. Because remember, 1 angle 180, again, that's 180 degrees is -1. Okay, so that would be 0.7132, angle negative 7.126 degrees. And once again, I'm in degree mode just to make sure of that. Okay, so I'll check that, and that is correct. And then the final step will be to do an inverse phasor transform to put this value of the SOT variable, the I0, into the time domain. Because after all, we're always trying to get an answer in the time domain ultimately when we do phasor analysis. So here we do need the omega value. Remember that whatever multiplies t is always omega. It's never f. I mean, it could be 2 pi f, but here I want omega basically. So that's 4 kiloradians per second. So I enter that as 4,000. And remember, you cannot put a metric prefix in this text box. So just enter that as 4,000. And then the phase angle is at angle negative 7.12. I'll just round it. 7.12 rather. And then the magnitude is going to be 0.7132. And so we check that. And again, the magnitude of the sinusoid is the magnitude of the phasor, and the phase angle of the sinusoid is the phase angle. And remember, we always use cosine here. If you're doing this by hand, you have to remember that we always use cosine function for inverse phasor transforms, never a sine function. That's just the way phasors are defined. Okay, so that is correct, and that's been added down here to the display. And that basically completes the problem. You also can get a detailed explanation if you wanted to understand this Kcl equation better, if you're not sure about that, or the SOT variable equations. So we can always click yes there and get a detailed explanation of those things, as well as if you wanted to know about the constraint equations, those are explained here. So that concludes this problem.